Okay, welcome, Erez and Alexia and Estefani and Rigny and Mafambi and Antonio and Adam and Bruno and Diego. Thanks for coming. As I mentioned, today is going to be all about quadric surfaces. But before we go into that, let us look at the quiz. Okay, so here's the quiz. And the first question is find the parametric equations for the line that passes through the points 412 and 130. Okay. So in terms of going over questions, that happens after the quiz. So we'll go over the questions of homework, but after I finish the quiz. Just want to get through the quiz while it's still really fresh in your minds. So let's take a look at parametric equations. How do you find parametric equations of a line given 2 points? What's the first step?
Find the vector by subtracting the second points or the first points from the second points.
Yeah, I call that the slope vector. So I'm just going to call that M is equal to, you take 130 and subtract 4, 1, negative 2. And hopefully that's easy for everyone. So 1 minus 4 is negative 3. 3 minus 1 is 2. And 0 minus negative 2 is also 2. Any questions on finding the slope vector? Okay, we also need to find the kind of like an intercept, the t-intercept. And what is that? That's easy.
Just use the first points, I suppose.
Yep. 4, 1, negative 2. And then you just follow what you learned in 7th grade or something, maybe 8th grade. And that is basically y equals mx plus b, but we're going to call it x comma y comma z is equal to m, which is negative 3 comma 2 comma 2. And it's not x, but t plus b, which is 4, 1, negative 2. And then finally, I asked you to find parametric equations. So that means we need to find x of t. What's x of t? Not supposed to be too hard. Yeah, negative 3t plus 4. And then we need y of t. And what's y of t? 2t plus 1. And then z of t. And z of t is 2t minus 1. Minus 2, sorry. And that's all there is to that one. Any questions on that? Okay, now let's move on to question 2. Question 2 is find the equation of the plane that contains these 3 points. So to find the equation of a plane, we need to find 2 vectors on the plane. And how do we find 2 vectors on this plane? So how do we find a vector on the plane? Yeah, we take the displacement vector, which means we take maybe the second point minus the first point. So we take negative 1 minus 2 is negative 3. Then we take 2 minus 3 is negative 1. And then we take 1 minus 5 is negative 4. And then w, another vector. Same idea, but instead of choosing the first 2 points, how about the first and the third point? Okay, as long as you choose the different ones. You can't choose the first 2 ones twice. So then we take negative 2 minus 2 is negative 4, comma, and then 0 minus 3 is negative 3, comma, and 4 minus 5 is negative 1. Any questions on this first step? Okay, what's the next step? What's the point of the, what's the purpose of those two vectors? What am I trying to get? Who remembers? Yeah, we want to take the cross product of the two vectors because the cross product of the two vectors on the plane will be normal to the plane. Exactly. So now let's take V cross W. So I'm going to write I, J, K. And then -3, -1, -4. And -4, -3, -1. I take that cross product. So let's find the I component. That means we get rid of the first column, first row. -1 times -1 is 1. 1 minus 12 is -11. So -11I. And now the J component. So we drop the second column, first row. You get 3 times 1 is 3. Minus 16 is -13, but it's negative, so it's positive 13, J. And now we take the K component. We get rid of the first row and third column. You get 9 minus 4 is 5, so plus 5K. Okay, and that's our N, our normal vector to the plane. Okay, what's the next step? As I mentioned 3 days ago, it's a very step-by-step process. Find D. I'm not sure what D is here. Yeah, it's time to actually write down the equation. And the idea is we have a normal vector, which means that you take that normal vector, which is, I'm going to write it as a vector in pointy bracket notation. So -11, comma 13, comma 5. And then we dot it with x minus a point. And it doesn't matter which point you choose as long as you're consistent. So x minus, how about the first point? 2, comma y minus 3, comma z minus 5 equals 0. And now we take the dot product. So we get a -11x plus 22. And then we have plus 13y. And then we have minus 39. And then we're going to have plus 5z. And then we have minus 25 equals 0. And you don't have to, but I'm going to clean this up a little bit. We get -11x plus 13y plus 5z equals, and 22 minus 39 minus 25 is 42. -42, and move it up as a positive 42. Any questions on the equation of the line? Any questions on the step-by-step process? You could also just plug in a point in. I'm not sure what you really mean by plug in a point. I don't know where you'd plug it in to find 42. Oh, I guess you could do that, but I like using it this way because that forces you to truly understand what it means to be a normal vector. And what it means to be a normal vector is if you dot that vector with any point on the plane, you get 0. So that's why I like doing it this way, because this way actually comes from understanding the plane instead of just kind of memorizing some steps. And the idea is the cross product always gives a normal vector. The normal vector dotted with a point on the plane is 0, and you just do it. Okay, let's do the third one. Find the angle between the planes 2x minus y plus 3z equals 6, and x plus y minus 2z equals 3. Okay, so we have two different planes. We want to find the angle. So what do we need to find first before we can even jump at the angle? What do we need to get out of these two planes? Yeah, two vectors, but in particular the normal vectors. So I can call it n1 for the normal vector for the first plane. That's the coefficients, 2, -1, 3. And n2 will be the coefficients of the second one, which is 1, 1, -2. Okay, so now that we have the normal vectors, we want to find the angle. And the good news is, if you remember what happened earlier last week, how do you find the angle? Because the angle between the normal vectors will be the angle between the planes, kind of by definition. And do you remember how to find the angle between two vectors?
The arc cosine of the dot product of the two vectors over the magnitude of the two vectors times each other.
Great, perfect, perfect. So let's find the dot product, n1 dotted with n2. And that's equal to, well, let me just write it out. That's 2 plus -1 plus -6. And that is equal to -7. Any questions on the dot product? Okay, then we need to find the magnitude of n1. And that's the square root of, oh, it's -5, not -7. Sorry about that. That's the square root. Okay, it's the square root of the sum of the squares. So that's going to be 4 plus 1 plus 9. And then that's 14, or square root of 14. Any questions on that? And then we need to find the magnitude of n2. And that's the square root of the sum of the other squares. Square root of 1 plus 1 plus 4, which is square root of 6. So then finally, we can say that our angle, I'll just use the word angle, is going to be the arc cosine of the dot product, which is -5, over square root. And remember, the product of two square roots is the square root of the product. And 6 times 14 is 84. Okay, and I do not even imagine expecting you to know that arc cosine by heart. Good luck. Any questions at all on finding the angle between two planes? Any questions?
I have a question.
Sure.
The homework had it as an absolute value for the top portion of the fraction. And then I don't know if that was just me or I could be wrong.
Yeah.
Oh, okay. Thank
So
you,
it's
Adam.
so actually, since we're doing an arc cosine, you can kind of get away with either way. Because if you remember, the arc cosine of theta and the arc cosine of negative theta are the same.
Okay.
Does that make-
Yeah. Sorry. Yeah.
Yeah, so it's fine to have an absolute value, but you don't need the absolute value. That's just, if you don't like negative signs, then put an absolute value, and that's no problem. Does that make
Okay.
sense?
Yes. Thank
Yeah.
you.
And that was just a little trig identity that says that if you want to get rid of the negative signs with cosines, you can do that. And that's all that is. So the book said you can make it easier on yourself and get rid of the minus sign. Okay.
Also, in the homework, there was repeatedly in this type of problem, they'd ask for the acute angle.
Right.
And so I found that and they're all in degrees. So I would subtract the result from 180, and that would be apparently what they were looking for.
Yeah, so the idea here is when you're talking about an arc cosine, you can define it as the acute angle. So that's all you're up to you. That's in other words, just how you define an arc cosine. Yeah, so you usually do it as an acute.
Yeah, I just gave both in this case.
Yeah, yeah, but in this case, my guess is it might be acute anyway. Because if you take square root of 84, that's a little more than 9, and 5/9 is close to half, and you're going to get an acute angle on that one. So I think you would get it anyway as your standard, angle on this particular example. Yeah, and usually you want the acute, but either way works. Okay. So yeah, what is that angle? That just depends on how you want to look at it. And either are kind of correct. Any other questions? Just note, by the way, if the homework asks for the acute, you need to make it acute. Because remember that computers are not flexible. If you don't get exactly what it's asking for, it is not happy. Whereas for me, if you show your work and you get what I got, that's good enough. So it's a difference between humans and computers. Any other questions about this? Okay, let's go and jump into the Q&A time. So I know way back when there was a question about a homework problem, but you have to let me know what the problem was. Remember the problems are randomized, so you can't just say number 7 because everyone has a different number 7. So, but if you have a question on the homework or any other question, this is the time. Questions? Yeah. And of course, I have office hours after class, and I can always answer after class too. But if there's questions, I'll be happy to answer questions. Yeah, I think it was Bruno too. Bruno, are you still around?
I'm still around. I had questions about the homework. Is it right if I can share my screen for it?
Yeah, I have to unshare. So you have to ask me so that I can unshare. Only one person's allowed to share at once. So let me stop my share and you can share your screen.
All right. Let me do so. All right, so this was the question that I had on one of the problems.
Uh-huh.
And
okay. Wait, let me read it. Find the perpendicular distance from the line given by the parametric equations to this point. Okay. So we have the line and the point, right?
Mm-hmm.
And remember we had a formula. Did you remember how the formula worked?
No, I don't remember how the formula worked.
See, that was like the whole, without the formula, you have like very little chance. So the idea here is, and it basically came from drawing a parallelogram, is you find a point on the line, and hopefully in less than a second, you can find a point on the line, can you?
Point on the line?
Hmm?
Let me see.
Just by
No,
reading?
it's not hitting.
You don't know a point on the line? How about -2, -4, 5?
Oh, no.
Right.
Sure.
Does that make sense? That's always a point on the line. That's the initial point. So I like to use the initial point because it's really easy to find. Do you agree?
I agree.
Okay, so we have a point on the line, okay? And we want to find the perpendicular distance from the line given the parametric equations. And if you remember that if you take a point on the line and then you look at the vector, basically you look at the vector from that point from -2, -4, 5 to the given point 0, 6, 1, then that's a vector, right?
Right.
And you're going to look at the projection of that vector onto the line. And then you look at the distance between that projection and the vector. Does that ring a
Oh.
bell from Friday?
That's ringing a bell now.
Yeah. So we
Now
had
I see it.
we had an equation. So the projection equation, if you remember, the projection of V onto W or whatever was V cross W divided by the magnitude of W times W. Do you remember that?
Yeah, I remember it.
Right. And then you find the distance from, so then you find the distance from that to the point. And
I
then
see.
you multiply the distance from -2, -4, 5 to that.
Okay, I see now. I see.
Okay. So does that make total sense?
Yeah, that makes total sense.
Yeah. And if you look, I think it was the last example. It could have been the second to last, but I think it was the last example I gave on Friday. And that should be recorded. Well,
Okay.
it's not these numbers, but the same idea.
I see.
Okay, great.
Thank you. Here, let me move
Other
on.
questions? Any other questions? If not, let me share my desktop anyway. And I have a question for you. Okay, it sounds like an easy question, but it's actually really hard. What's the definition of a cylinder? What is a cylinder? And I know you're worried. Isn't it a plane you showed us the other day? Okay, cylinder's not used. I mean, actually technically a plane is a cylinder, but that's not the general definition. I mean, the cylinder that you know of, like a can, that's what you're used to, right? Okay, so pi r squared h. Okay, so pi r squared h is a formula, not for a cylinder, but for the volume of something we call a right circular cylinder. Okay, and a circle with a height, that's a right circular cylinder. Turns out to be a very special kind of cylinder. But we want to be able to handle what's called general cylinders. An object of rotation. I'm not sure exactly what that means. But it actually doesn't have to have rotation, it turns out. So I didn't expect any of you to come up with it. So it's not about rotating. So let me define what a cylinder is mathematically. Okay. So here is the definition of a cylinder. Let C be a curve in a plane. Then a cylinder is the set of all lines perpendicular to the plane that pass through that curve. Okay, so that's the definition of a cylinder. I did not expect any of you to come up with that. But I did expect you to know kind of the classic example of a cylinder, which is a right circular cylinder, where in this case, the curve is a circle. And then the perpendicular lines through that circle will give you the cylinder. Okay. And an equation of just two variables is always a cylinder. And most of the time you deal with an equation of just two variables and let that be. So I think the best thing to do is to picture it. And honestly, I'm much better with computers than I am with art. There's a very good reason that art was not my major. So I am going to take this guy and let's take a look at some examples of cylinders. So let's do the one that you're all used to. And that is, how about the right circular cylinder of radius 1, x squared plus y squared is equal to 1. And my guess is you're used to this guy, right? You see this, and if I asked you what the shape of this was, what do you call this? Am I right that all of you would have said cylinder? Right? I hope so. I hope so. Okay. On the other hand, what it says is that it doesn't have to be a circle. It could be any curve. So for example, how about a y equals x squared or y minus, we'll just do y equals x squared. Okay, when you look at that, y equals x squared, what do you think y equals x squared is? You could put some words in the chat or a word in the chat. Okay, so you think it's a parabola. Okay, because that's what you grew up with, right? Okay, is that you learned about this being a parabola. Okay, but now, just to be different, we're changing context. So if you're looking at y equals x squared in the xy plane, yeah, that's a parabola. But now we're moving to 3 dimensions. And we're not going to look at y equals x squared in the xy plane. We're looking y equals x squared in the xyz 3-dimensional space. And that changes things. So I'm going to click enter. And now we can see this is not just a parabola. Do you see that? In fact, what do you think how would you describe this? What we're looking at here in words. If you had to describe to someone who's not a mathematician. Okay, trough, that's a good one. Okay. So you've seen these things. This is not something you've never seen before. Okay, this shape happens a lot. It's not a parabola because it's 3-dimensional and parabolas are 2-dimensional. But it is the surface that corresponds to the equation y equals x squared in xyz space. And the name what we're going to use for the language in math is parabolic cylinder. Because it's a cylinder, because notice that we take this parabola and take any point on the parabola and then take a perpendicular line to that point, and that's going to be on this parabolic cylinder, whether it's this line here or this line here. So that's a parabolic cylinder. Any questions on that? Okay. By the way, it doesn't have to just be y and x. As long as it's only 2 variables, you get a cylinder. So it could be something like, how about z minus the cosine of y. Okay, that's a cylinder also. And that's a cylinder because we're missing a variable. Do you see that? There's no x here. And what happens though, when you're missing x instead of missing z, is the perpendicular lines are parallel to the x-axis. So here's our x-axis, and here's all our perpendicular lines that make up this cosine cylinder. Any questions on that? And let me I would better have more. How about 100? Might take a while. Yep, there it is. So this is a cylinder also. Looks very different, doesn't it? So this is a kind of a cosine cylinder because you take the cosine curve and then you take perpendicular lines to that cosine curve. And that's a cylinder. What does that look like, by the way? Where have you seen this? In the real world. Yeah, waves. Okay. This is what waves look like, whether it's in the ocean or in the lake, or even taking a blanket and flapping it up and down a little bit. It's going to look like this. Okay, so it's very important, these three-dimensional cylinders. They come up a lot. They're really easy to identify. They're obviously, at least if you watched, they're easy to draw when you're using Calcplot 3D. Hopefully you agree. But they're also not that bad to draw by hand because you just draw the curve and then you draw some perpendicular line segments. And then typically you draw the other side of the curve. Any questions at all on understanding this general definition of a cylinder, which is very different than the cylinder that you grew up with? Any questions on this definition? And as I mentioned, the easiest way to identify a cylinder for most cases is it's something in R3 that's missing a variable. If it's missing a variable, you get a cylinder, period. Any questions? Doesn't look too bad. Okay, so the next thing I'm going to talk about is very complex. We're not going to do all of it. We're going to do some of it. We're going to do some special cases. But I want to mention, we've talked about planes, and planes basically look like AX plus BY plus CZ equals D. Do you all agree? That's a general equation of a plane. So what do you think the next level up is going to be after planes? So let me remind you, a plane is AX, I'll also do it pretty, AX plus BY plus CZ equals D. Okay, a plane is a surface. A plane actually is a surface. So that wouldn't be the next level up. That would just be more general. So what do you think the next level up of difficulty is for surfaces after planes? So let me ask you this. Let's go back to 8th grade and maybe 7th or 6th grade. You learn about lines. And you spent some time on lines. You learned y equals mx plus b. Okay, or ax plus by equals c is probably a better way of talking about it. And then you went to the next level. What was the next level after lines? That you did in beginning algebra. Curves are all levels after that. Just one little step up after a line, which is still pretty much harder. Circles came much later, actually, because circles are y equals the square root of, a squared minus x squared, and that's kind of messy. Something a lot less messy came after lines. Anyone remember? I'm sure you all do, but you just aren't thinking about it. I don't see y'all jumping in. The next level was parabola. Hopefully you know what a parabola is. If not, then you don't belong in this class. Okay? But in particular, the reason why it's the next level is planes are first degree, right? It's really ax to the first plus by to the first plus z to the first equals d. How about a parabola? What's a general parabola? Yeah, it's second degree. Okay. So it's second degree. But we could do parabolas. But sometimes you want to go even more, a little bit more general, keep it second degree and make it more general. So if you remember the second degree polynomials in two variables, that would be things like x squared plus y squared equals 9, or x squared minus y squared equals 1, or x squared plus y squared over 4 equals 1. Do you remember what you call those? The parabolas, the ellipses, the hyperbola, the circles. Do you remember the name for all of that combined? Again, this is a review. Maybe you don't. Conic sections. Does that ring a bell? I hope so. Those are called conic sections. And the way to write those are ax squared. And I'm going to go more general than you know. Plus by squared plus cxy plus dx plus ey equals f. Does that ring a bell? That any equation that looks like this in 2 dimensions is called a conic section. And it'll always either be a hyperbola or an ellipse or a circle or a parabola. And we make sure that A, B, and C are not all 0, because if there's all 0, then you get a plane. So we usually don't put those in. Does that ring a bell at all? I hope so. Here's the part you probably didn't do. You probably didn't do the CXY. So that is more general than you'll learn in high school. Okay, but I'm telling you, the CXY is part of it. And to understand it, you need a lot more math, more than we're going to do in this class. All right, so we're jumping now into 3 variables, because what we're doing in this chapter is all about R3, not R2. So we're not just going to have X's and Y's, we're going to have X, Y's, and Z's. And again, we want to start out from a plane, thinking about a plane, thinking about conic sections. We're going to jump from a plane to the same idea, but you're allowed squares and products. How many terms do you think you're going to get? Any thoughts? Okay, 10 I hear, so let's see. Okay, so here's our definition. A quadric surface. It's kind of like quadratic, but we call it quadric. Has equation ax squared plus by squared plus cz squared. So we're adding a z component, plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals 0. And we're going to say that not all A, B, C, D, E, and F are all 0. If those are all 0, you just get a plane, and we don't call that a quadric surface. So that's the definition. Very easy to come up with examples. Just throw one in. How about How about 2x squared minus, how about 3z squared plus, how about xz minus yz plus x minus z plus 1 equals 0. Do you agree that's a quadric surface? Okay, so now comes an interesting question. Okay, this definitely fits the bill. Hopefully you know how to identify something as being a quadric surface. Here's a question that good luck on, okay, without technology. What do you think it looks like? Any thoughts? Any guesses? So a guess is fine. Maybe something with 4 angles in it? Okay, possibly. All right, well, there's one way to try. So I will let you know. Hyperbola and one plane and something else on other. Okay, so we'll see. We'll see. So here's something I want to give you a heads up on. You will possibly never learn how to identify this by hand unless you become a mathematician or possibly a physicist. Because, or if you're really good at linear algebra next year, that's the other possibility, because it's actually a really hard question. So we actually are not going to learn today how to do this by hand, but we can do this with a computer. And a copy and paste, I don't know if it'll work, but we'll see. Pretty good. I just got to put the squares in. And let's take a look. I need to go to 2. Let's go to 2. Is this what you guessed? Okay, you're pretty close to saying a hyperbola on one and something else on the other, but actually it's a hyperbola on one and it's a hyperbola on the other. This is called a hyperboloid, and we'll get to those in a bit. And it's called a hyperboloid of 2 sheets because there are two hyperbolas that we're looking at, and they're disconnected from each other. All right, here's what we're not going to do. I'm never going to, in this class, going to expect you to see that equation and ever come up with this graph or even describing what it is without using a computer. Okay, but there are going to be some that we do have to do. So let me note a bunch of things. So here are some kind of things about the class. Okay, one, there we go. So one, we will always let or have D equals E equals F equals 0. Okay, and the reason for that is, any guess for this class? Is it offset? No, that's going to be the others, actually. We'll get to the offset in a bit. Okay, so here's the reason. Because it's too hard for this class. Okay, preventing headaches, maybe. Yeah, it might be one way. Okay, preventing giving up is probably even a better way. This is something you're going to be doing in linear algebra if you take that class, which is 5th quarter calculus, kind of. So we're going to stay away from that. And what those do, the D, E, and F, by the way, turns out there's a rotation involved. And I'm just not going to go there. So 2 is if G, H, or I are non-zero, how can we get rid of them? Any suggestions? It's messy, but it's not anything harder than algebra, than just probably intermediate algebra. Yeah, then we can complete the square. and get rid of them. So you complete the square, get rid of them. The G, H, and I, all they do, these just shift the surface. Okay, maybe in number 1, I'll say these rotate. Okay, so D, E, and F rotate the surface. G, H, and I shift the surface. So shift meaning a translation, just moves it to the left or right or up or something like that. But it doesn't change something that looks like a hyperboloid and turns it into something else. That's not going to happen. Okay. Whereas number 1 changes everything. I'm going to write and more. And I'll just stop it at and more. Any questions on kind of the basics of what these letters do? Okay, so that gives us, so then we can work with something much simpler. And the simplified surface, the idea is we can get rid of a lot of it. So we can get rid of all of these guys. And that's a lot easier, isn't it? All right, so now comes what's interesting. Now we want to say, let me write or. If one of A, comma B, comma C is 0, then we keep the corresponding linear term. Because if you don't have the corresponding linear term and A, B, or C is 0, you have a cylinder. But actually, it turns out you get more interesting stuff if, let me write one or more corresponding linear terms. So the idea is if one of the quadratics is 0, you want to keep its corresponding linear. Any questions on that idea? Okay, so now let's do a specific type. And actually, before I do that, I have a question for you, a little story. Okay, there's some debates. There are some debates. One side says that the Earth is flat. Okay, another side says the Earth is spherical. Okay, is the spherical Earth correct? Right, if you have to listen to the debate. Yeah, the answer is no. The side that says the spherical Earth is not correct. Okay, that does not mean it's flat, by the way, just a big note. Okay, the Earth is not spherical. And it turns out it's not perfectly elliptical. And you know that if you're in Tahoe, how come? Yeah, we have mountains. Okay, we have mountains. And even if we didn't have mountains, you'd still have valleys, you'd have waves and things like that. But if you kind of ignore the mountains and the waves, it turns out that it's still not that spherical. And that actually affects a lot of things in terms of climate, for example. The tallest mountain on Earth, measured from the center of Earth, is it's not Mount Everest. Okay, and that's because the Earth is not spherical. And actually, because of that, and Mount Everest is farther north, then in Central America, I always blank on the name, it's hard to pronounce too. Some of you might know, but there's a really tall mountain in Central America that actually is taller measured from the center of the Earth than Mount Everest. And that's because the Earth bulges at its center. And anytime you have something that's spinning, so a little physics or geology, whatever you want to call it, if you have something that's spinning that has some kind of liquid in it, so it's like if you take a water balloon and spin it around, it won't be spherical when it's spinning because it bulges at the center. And what you end up with is what's called an ellipsoid. So I want to note something. Let me give you the definition first. An ellipsoid is a quadric surface of the form x minus h squared over a squared plus y minus k squared over b squared plus z minus l squared over c squared equals 1. Okay, if you get to choose where the origin is, you can get rid of the h, k, and l. And you could just say x squared over a squared plus y squared over b squared plus z squared over z squared is 1. And that always works. I'm going to mention something. There are two pieces of the word ellipsoid. There's that part, ellipse. And hopefully you all know what an ellipse is. What is an ellipse? So what's an ellipse? Circle with different radii. That's a good kind of way of thinking about it. We don't usually say that because if you have a circle, you have a circle. Circle only has a radii. But your idea is right. The idea is x squared over a squared plus y squared over b squared is 1, an ellipse centered at the origin. So we see that if you get rid of actually any of the variables, we get an ellipse. On the other hand, there's oid. So oid brings it to 3 dimensions. And it's kind of like a circular-ish thing, or it's also kind of part of ellipse. So it means that if you look at it from the other direction, in other words, you get rid of a different variable, then you also get an ellipse. So if we get rid of x, if we get rid of this first term, what's left is an ellipse. Do y'all agree? Okay, if you ignore the x-axis. If you don't, it's an elliptic cylinder. If you get rid of the second term, we get an ellipse. And if you get rid of the third term, you get an ellipse. And that makes an ellipsoid. Okay, when you get rid of one of the variables, when you kind of take the projection on to a plane, the xy plane, the yz plane, or the xz plane, then that's called looking at the trace. So let me write that down. The trace of a circle is a projection of it. Sorry, the surface, not circle. Projection of it onto a coordinate plane. So notice a projection of an ellipsoid is always an ellipse. Very easy to take a look at an ellipse. An ellipsoid, I mean. So let's say you have x squared over 4 plus y squared over 9. How about plus z squared equals 1. So we can see we have this ellipsoid. Let me make these instead of 2, how about 4 out? And instead of 10, let's make it 30. Make it a little prettier. We need negative force. There we go. Okay. And what does this kind of look like? It kind of looks like a discus in a way. A little bit. Okay. They come up in different places. So ellipsoids definitely could come up. By the way, if we made it instead of a 9, let's say make it a 5. How about over? There we go. Now it looks a little more Earth-like, right? So it's not quite a sphere, but a little more Earth-like. Okay. By the way, is an egg an ellipsoid? What do you think? Okay. Yeah, it was a trick question. The answer is no, even though I know most of you probably think it is. It turns out an egg is mixed not with a cone. It's mixed with a hyperboloid, which we're getting into next. And that's really important. I don't know if we have any structural engineering pre-majors here or architectural engineering. Any of you doing that? Or civil engineering? But they need to know this kind of stuff. And that's because hyperbola, an egg shape, which has hyperbola on bottom and top, it turns out, and then mixed with an ellipse in the middle, turns out to be the most sustainable and strongest structure. So if you're building something and you want to make sure it doesn't break, and chickens are very good at making sure their eggs don't break, or at least genetics is in Darwinism, that's how you do it. So an egg is not quite an ellipsoid. Okay, but the Earth is pretty close, pretty much an ellipsoid. And this looks pretty much like the Earth. Any question on ellipsoids? Okay, so then comes the next group. So just a note, what makes us special? See if you remember, what's the difference in terms of the equation, the main difference between an ellipse and a hyperbola? Yeah, exactly. So a hyperbola has one negative and one positive, okay? Whereas an ellipse has two positives. So now we're going to move on and say, well, what if we took one of those positives and made it negative? So let's take a look. And what we get is what's called a hyperboloid of one sheet. And that's a quadric surface where it's an ellipsoid, except you replace one of the positives with a negative. So that you get all three choices. And if it's centered at the origin, you can ignore the H, Ks, and Ls. And that's a hyperboloid of one sheet. Okay, so let's do an example. Always good to have examples. So what if we had x squared minus y squared minus y squared plus z squared equals 1. So I tried to pick a really easy one. So notice that here there's no shifting, so the center's at the origin. A, B, and C are all the same, but we have a minus for the y squared. Let's take a look. So notice what happens if you get rid of the x squared term. Then what does it look like? So if you erase that, then what do you get? Yeah, that's a hyperbola or a hyperbolic cylinder, but a hyperbola if you're thinking 2 dimensions. What if you get rid of the z squared? What do you get? Yeah, that's also hyperbola. How about if you get rid of the y squared? What do you get? Yeah, then you get a circle. Okay. And by the, had there been a number in front of z squared, you get an ellipse. So the you could see the kind of hyperbo. That means you get like a hyperbola in some of the traces. And then you have oid, and that means a circle and ellipse in a different trace. So that's why there's a hyperboloid, not a hyperbola, and not a sphere or a circle or an ellipse, but a hyperboloid, because depending on which one you erase, you either get an ellipse or you get a hyperbola. And a sphere is a special kind of ellipse, by the way. Okay, or a circle is a special kind of ellipse, is what I meant. Let's see what they look like. And let's not go all the way to 4 this time. This one, I think 2 is better. Okay, have you seen anything that looks like this before? Have you seen this shape in the real world? Yeah, nuclear reactor. Yeah, so if you look at a nuclear reactor, that's the shape. Okay, and I'm actually not a nuclear engineer, so I actually have no idea why it's that shape, but I trust the engineers that there's a reason that they didn't just do it by chance, that it was probably the best shape for them. And my guess is you trust them also. So that's the shape, and it does happen. There's another place where this happens, which is cool to me, and that's because I'm not a big, I'm okay with nuclear reactors, but it's definitely not my specialty. The other place you might see this is in advanced physics. Do you know where this comes? Okay, this comes up in what's called the general relativity light cone, when you have a moving object, which I'm not going to get into. But it does come up. The other place you might see it is if the center of this hyperboloid of one sheet was a big star, and something came in like this, then you're going to end up, or sorry, the star is here, you're going to end up with this path, and that'll be the path of an object that does not get put into orbit when it gets closer to the star. So it's kind of cool stuff. So it does happen in astronomy, and it happens in nuclear engineering for some reason. Don't ask me why, because I have no idea, but it does happen. Notice we call it one sheet because you all agree this is connected. That if you're on one spot of the hyperboloid and your friend is on another spot, you can get to each other without leaving the hyperboloid. Do you agree? So that's why it's called a hyperboloid of one sheet. On the other hand, now let's go into the next definition. You could take the same thing, and instead of changing one of the signs to negative, change 2 of the signs to negative. Okay, and that'll still give you a quadric. And it turns out that's a hyperboloid of 2 sheets. So basically it looks similar to hyperboloid one sheet, but if in this case, the traces are interesting. Notice if you get rid of the first term, this is tricky. What happens if you get rid of the first term? On this first example, what does it look like? Is it a hyperbola facing it down? No. The hint is it's tricky. The answer is it's nothing. Because negative this stuff squared minus this stuff squared can't be 1. Because this rest of stuff is only negative. Does that make sense? Can't have a negative number equal 1. No matter how hard you try. Okay. By the way, you don't get into complex numbers in our class. So complex geometry is much harder. I'm not going there. But so this is a nothing if you get rid of the first term. On the other hand, if you get rid of the second term, you get a hyperbola. And if you get rid of the third term, you get a hyperbola also. So it's still hyperboloid, but it's of 2 sheets. So now let's just change. It's really easy to change. You just add a negative sign to either the pluses, put 2 negatives instead of 1 negative. And there's a hyperboloid of 2 sheets. Okay. And what's going on here is that if you look at the plane, in this case, the YZ plane, this surface doesn't hit the YZ plane. It's nothing on the YZ plane. And that's what we saw in the equation also. There's no intersection into the YZ plane. And that's why that plane cuts the hyperbola into 2 separate surfaces. And we call it a hyperboloid of 2 sheets. Any questions on that? Pretty stuff? All right, let's do the next example. Now what we're going to do is we're going to get rid of one of the squares. I don't know why I got this twice. There we go. So an elliptic paraboloid is a quadric surface where there are exactly 2 squares when solving for the linear term. The signs in front of each square are the same. So let me give you, it's easiest done by example, and then you'll get the idea because there's a whole bunch of cases, but the examples show you what's going on. So for example, z equals x squared plus 2y squared. Okay, and I'm going to write it this way. You could also write it as x squared plus y squared minus z squared is equal to 0 or 1 if you want, whatever you want to choose. Okay, let's see what's going on here and why do we call this an elliptic paraboloid? What if you let z equal 1? What do you get? So we're looking at traces now. If z is 1, what picture do you get? So if z is 1, what do we get? What shape? Yeah, you get an ellipse. Okay, what if x is 1? What do you get? Yeah, you get a parabola. What if y is 1? What do you get? Yeah, you also get a parabola. And that's why we call this an elliptic parabola, because we have one of the traces is an ellipse and the other traces are parabola. So it's an elliptic paraboloid. And oid means 3 dimensions, basically, or it's a surface. So let's do this one. Z equals x squared plus 2y squared. And take a look. What does it kind of look like? What does it kind of look like in the real world? Yeah, kind of like a ball. Kind of like a ball. Okay. And so bowls are basically paraboloids. They're not perfect, but close enough. Okay. And by the way, if we switched it, and let's suppose we, instead of got rid of the z squared, let's say we got rid of the x squared. So then let's say we had x minus y squared. Let's say minus 2z squared equals 0. Does it look much different? How's it changed? Yeah, it's the axis. It's just which is x, which is y, which is z. Okay, any questions on an elliptic paraboloid? So that's when you have two of them squared, the other one's not squared. You get something that looks like this. Okay. By the way, what do you think will happen if I get rid of that minus and make that a plus? How's that going to change things? And the key is if you let x equal 1, now what is it? It's not going to be a flip. If you let x equals 1, what shape do you get? Not circular. Y squared, z squared minus y squared equals 1. The hint is not an ellipse. What is it? Maybe I'll hit enter and then you'll see. What do you see? Yeah, this is a saddle. Okay, saddle is kind of the, the way you learn it before you learn heavy math. Okay, hyperbolic paraboloid instead of elliptic paraboloid. So we still have that parabola right here, but now you have a hyperbola also. So that's why it's a hyperbolic paraboloid instead of elliptic parabola, because if you get rid of the x, it's a hyperbola. But if you get rid of the y or the z, then it's a parabola. Any questions on that? Okay, then finally, the last one is a cone. So a cone is a surface of this form. What's special about this one? What's different with these compared to the others we looked at? There's something very special. Yeah, we have the equals 0. There's no constant term anymore. So now we have an equals 0. And I can draw, I can let the computer do a cone. I'm going to do all these centered at the origin. Hopefully you know how to complete a square if you need to. But we could do a cone. So let's do a cone. So let's suppose we have, how about x squared minus, let's make that x, make it an x squared. X squared minus y squared plus 2z squared equals 0. Okay, so notice you get something different. Let's play around. Do you see the cone? Okay. It's different than an ice cream cone because it's got a top and a bottom, where ice cream cones only have a top. So you just got to get used to that. As a child, you learned a cone was only half of this, but it turns out a cone is all of it. Notice that the the y-axis is what the cone rotates around. And that's got the negative. Do you see that? If I take that negative and put it on the z-axis instead, then now we have a cone, but it's rotating about the z-axis instead. So it has a z-axis symmetry. Any questions about a cone?
Larry, would you consider this one sheet or two sheet? Is it continuous?
Cones are not, they're continuous, but not differentiable. So we don't even go there. It's a good question. Technically it's connected, because if you're over on one up here and your friend's down there, you can get to your friend. Does that make sense? But I usually don't even go there with cones, because cones have a top and a bottom is an easier way of saying it. We usually don't talk about sheets, because cones don't have that differentiability issue, differentiability. So everything goes wrong with cones. And there is something called the light cone, and that's in regular relativity. And then that tells you what you can see in the universe. And that's the cone. We can't see anything outside the cone. So if something's over here and you're over here, you'll never see this area. That light won't get to you. Okay. So let me let you know. So we've now talked about all kinds of different quadric surfaces, cylinders, ellipsoids, hyperboloids, paraboloids, and cones. So you should be able to recognize one from another and know from the equation without using a computer to draw the graph, because on the exam you won't be allowed to. You should be able to recognize what the shape is without using a graphing computer. Just to note that by looking at the squares and the negatives. Okay, let me stop my share. And we'll call it a lecture.